Let's talk a little bit more about the meaning of the CP values and the meaning of the CPK values. I've talked about them before, but I'm just trying to summarize them here. The specification width is only 1/2 the tail-to-tail difference. So there's your CP equals 0.5. If your CP is equal to 1, it means that the tail-to-tail of the bell curve is exactly the specification width. But remember, with the CP, it does not take into account where this average is centered. It could be centered up here and you're going to get the same CP values. A CP of 2 looks like this, which means that the tail to tail of the bell curve is 1/2 times the specification width, or I could say it conversely, the specification width is twice this. The meaning of CPK values, while the CP simply looks at the upper specification limit minus the lower specification limit as compared to the width of the bell curve, CPK essentially looks at the half of the bell curve that is closest to one of the spec limits. The CPK value gets worse as you move from left to right on the diagram below. This CPK is less than 1 because you have stuff outside specifications. This one gets worse. Even though the width gets better or the CP gets better, the CPK continues to get worse. Even though the CP of the far right bell curve is better, narrower, not the CPK, it will likely have a worse CPK value since the process average, the center of the bell curve, is so much closer to the upper specification limit. So, kind of trying to draw this to a close to a certain degree is the relationship between the specifications, the average, and the standard deviation on the CP. If we widen the specifications, the CP value increases because it's upper spec limit minus lower spec limit. If that gets wider and that's on the top of the fraction, you're going to have a higher CP value. If we reduce process variation, our standard deviation goes down, the CP value also increases because on the bottom of the CP formula, that number is going to get smaller, which makes the overall thing bigger. As mentioned earlier, the process average has no impact on the CP value. Now let's talk about the relationships with regard to CPK. If we widen the specifications, the CPK value may or may not increase, depending on where it's being widened at. If you have a problem on your lower specification limit and you add space to the upper specification limit, it's not going to make a difference to your CPK because the problem is still in the lower specification limit. If we widen the specification limit nearest the process average, the X bar, only then will the CPK improve. If we lower the lower specification limit, then that's going to improve our CPK. If we reduce process variation, that is the standard deviation, the CPK value increases. Because the process average is a part of the CPK formulas, it impacts the CPK value. And there it is. So what does a CPK of 1.0, 1.33, 1.67 mean? CPK equals 1 means the process is capable of producing essentially all parts to specification if the process average remains unchanged. If you have a CPK of 1.33, it also means that the process is capable, but it also indicates that we have a little wiggle room with our process average, that is 1 standard deviation of wiggle room, before the process is no longer capable of meeting engineering specifications. 4 standard deviations divided by 3 standard deviations equals 1.33. You have that extra standard deviation of wiggle room. If you have a CPK of 1.67, it also means that the process is capable, but also indicates that we now have 2 standard deviations of wiggle room. 5 standard deviations divided by 3 standard deviations is equal to 1.67. You have 2 standard deviations of wiggle room before it goes out of specification.